Hey everyone, welcome back to MLWalks. In this video, we'll be discussing the top 5 dimensionality reduction techniques, and we'll also understand why do we need dimensionality reduction. So the key reason behind setting up dimensionality reduction is to simplify the data set from high dimension data to low dimension. Because once you have low dimension data set, then you can easily apply machine learning model and get a performance boost. What happens is when you have high dimensional data, there are very good chances most of the features in the high dimension data set would be noise, and once you project that into lower dimension, you will tend to reduce the noise and making sure that your model performs better. And another reason why you do dimensionality reduction is to make sure the data is more interpretable and you can visualize the data. And the key benefits reduces down to the curse of dimensionality. As I said, when you have high dimension, you will have large number of features, and most of those features don't add much value to your task, what you're trying to perform, whether it is any kind of prediction or anything. So, and it also becomes very difficult to build a model on top of it because it requires large amount of compute and also requires large amount of storage space. And it's like you have tons of zeros in your features and you want to store them as well, though they don't add any value. And since there are large number of features, so you will end up building complex model, which will also lead to overfitting. So these are some benefits of dimensionality reduction. So let's understand and implement the 5 dimensionality reduction techniques. So first we'll be looking at PCA and then tSNE, the UMAP, LDA and autoencoder, which is a neural network based approach for dimensionality reduction. So first we'll be importing the packages that are required. First is sklearn, which contains the dataset, then PCA for dimensionality reduction, then we have tSNE and then LDA. So for these 3 approaches, sklearn is enough. And for UMAP, you have to install UMAP package. And when it comes to building a neural network, you can either use PyTorch or TensorFlow. So here we'll be using TensorFlow. So let me import all these packages. So once we are done with importing of packages, what we'll do is we'll be loading the data set. So we'll be working with only one data, which is iris data set, and which has around 4 features and 1 target. So let me just, and what we do is once we load the data set and separate into X and Y, we normalize the data set with standard scalar. So let me run this as well. So it will contain around 4 features which we want to project into lower dimensional space with the help of dimensionality reduction. So while this is taking a little bit of time because I'm running it for the first time, so it is checking for whether CUDA is present or not, because TensorFlow will check for all these different dependencies in the backend, whether you have CUDA or not, and based on that it will enable certain flags and everything. So while this is running, let's see target names and then x.shape. So let's see, there are 4 features and 150 records are present. There are 4 target names, that is, these are the 4 different flower, I guess this is the name of the flowers. Not 4, that is 3. Now that is, it means like we have 3 classes. Now what we do is we get started with principal component analysis. So it tries to project the data in the direction of maximum variance. So in high dimensional space, wherever there is maximum variance in terms of data spread, it will try to capture that. And this works better when the relationship between the features are linear in nature. And in the iris dataset, PCA already gives some cluster separation, but classes still overlap. Okay, so here what we do is first we initialize PCA with n components is equal to 2. So out of 4 features, we are trying to project that 4 features into 2 features in the lower dimensional space. And then once we define this PCA, we try to fit it on our data set, which is X scaled. We do fit and transform, and then what we do is we just plot that. So let me run this. So if you see here, there is some clear linear relationship between some data points. That's why we are able to capture one projection here, which is easier to understand. And this is where you have some other projection or component, principal component present here, where there is some overlap as said. So this is how you do it with PCA. When it comes to tSNE, which is T-distributed stochastic neighbor embedding, it tries to understand the local neighborhood. It tries to focus on the clusters which are local in nature and tries to preserve them. Well, it produces well separated clusters and great for visualizing high dimensional embeddings. So it will also produce different distinct clusters, but may have like global distances may be distorted. So it may fail in when you have global relations. You want to understand the global relationship between embeddings. You might fail in when you are using tSNE. So it's clearly segregating these data points. Okay, so if you see here, and here also if you want to just understand this part, right, where we have tSNE declared here and we want to project it into two-dimensional space. Random state is 42, perplexity is 30. Okay, now this is our data and we apply tSNE on top of that our data set. Then what we do is we use again same plotting mechanism where you plot as a scatter plot tSNE on 0th dimension and 1st dimension. And this is the title and show. So it is very well separated clusters. Okay, we can clearly see these clusters forming. Okay, good for visualization and not for feature extraction purpose. And now comes UMAP, where this is better than tSNE when it tries to understand both local and global structure, and it is faster and scales for larger dataset. And it separates classes almost as well as tSNE, but keeps the intercluster relationship more faithful. So what you do is again you have UMAP and you pass in the two components you want to project into, and the random state as 42. If you want to replicate the results, you can keep the same random state, and then what we do is we create a reducer variable and then we fit that on top of our data set and we go ahead and plot it again as usual. So the similar to tSNE, faster, preserves global structure better. So this also able to segregate the classes perfectly in terms of clusters, and there is local and global structure being preserved. Now comes LDA, linear discriminant analysis. It works only when you have target label present. That is, you have this target which we saw earlier, right? 3 classes. So unless this is not present, you cannot apply LDA. So what we do is supervised method. This is a supervised method that uses class labels to maximize the separation. Best at separating classes when the labels are available. Okay, it's not possible to segregate or provide a lower dimensional data without classes. So what we do is we make use of labels to segregate the classes in a lower dimensional space. So how do we declare, right? LDA, then again we pass in the 2 components that we want to project into, and then we transform it. While we are transforming it, we are passing the scaled data along with the target variable. Then what we do is we just plot the graph, scatter plot, where we pass in our 0th and 1st dimension of LDA. So even here you can see we can have separate clusters are mentioned, but there are some amount of overlap as we have seen in PCA as well. So next comes autoencoder, which is the neural network approach for building or creating a lower dimensional space for your data. It learns a compressed nonlinear subrepresentation using reconstruction loss. This is while doing the training phase, we'll be having this reconstruction loss, and it is flexible and scalable for large data sets. On Iris dataset, the clusters are visible but not as sharp as tSNE or UMAP, since the autoencoder is unsupervised and trained only for reconstruction. So this is phase reconstruction. That is one of the approach where the phase reconstruction is one of the use case where we use autoencoder, where you have an encoder-decoder architecture where you pass in your input and you pass it to encoder and you send it to a bottleneck layer, which will be in lower dimensional space. and then you again project from lower dimensional space to decoder, and from decoder you get your output. So what we do here is, first we take our input, which is x scaled, and get the shape out of it, which is 4, which is your input dimension, and we are encoding into the 2-dimension space. And here we are trying to create our neural network where we have layers.input, and we say that the input will be of 4 dimension, and then we pass that input layer to a dense layer and transforming it to 8 dimensional embeddings. And then what we do is we again send it to the bottleneck layer, where it will be bottlenecked around 2 dimension. Then we again pass it to the decoder, which will be again a dense layer where it is 8 dimension, and then we are sending it to the output layer, which is the 2 dimension, which is 4 dimension again. So our main point is here where we have bottleneck layer, right? This is very important for us. So if you see here, this is where we create our neural network, and then we turn that into a model here. Models.model, we say input layer and output layer, and we create a compilation with Adam optimizer and the loss function, which is mean squared error here, and then we fit the model on scaled data. So here we don't use any labels, we just want to compress our data into lower dimension, and the epochs is 100, batch size is 16. And while you're doing this, if you see here, okay, since this is dimensionality reduction, okay, we are not interested in the output layer, which is this one. We are interested in the bottleneck layer where you have in 2-dimension space. The whole input is projected into 2-dimensional space. So which is 2 here, encoding dimensional. So here if you see at the bottom, extract encoder model will be taking out output from bottleneck, and that is your output. And then we pass, we are creating an encoder, and then we are passing it to scaled. It's something like what you're creating a model here. You're creating a model and you are trying to apply the model. And once you have applied the model, then you can just plot your model here. Okay, because what this will do, right? It will try to generate 2-dimensional output for the 4-dimension input that you give here. So let's run this. Okay, some issues are present. The DNN library initialization failed. Look at the errors above. So to overcome the DNN initialization issue, what we do is, instead of depending on GPU, right, what we do is we disable GPU for now, because we are not interested in utilizing GPU for a dimensionality reduction. So what we do is we just, before importing TensorFlow, we just add these 2 steps, import OS and turn the environment into -1 for CUDA. So once we are done with that, what we do is then we start running it again, where we have this model created and neural network created, and then we just run it. So now it is not using GPU for creating this neural network and getting the embedding space out of the neural network, which is the bottleneck layer out. So this is what the output of autoencoder looks like. So it just learns the compressed representation via neural network and flexible for large data set. Now if you want to use all the 5 output that we got, what we can do is we can just, okay, let me run everything first. So we have executed this one, let me run this one. So yeah, we have executed all the 4, 5. Now let us see the output here by combining them. So yeah, so this is the final result for all the 5 different dimensionality reduction technique. So here I think UMAP has the best segregation between the classes with clear clusters getting presented. Otherwise, what we can see is there is some amount of overlap that is happening here and there, a good amount of overlap. Though even in UMAP we have, but it's much more less compared to other techniques. Now coming to the key takeaways from what we have done till now is PC and LDA are good for linear structure when you have features which are dependent on each other, or when you increase a certain variable, the other variable tend to increase. So it is able to capture that with PCI and LDA, and it is fast and interpretable. And when it comes to tSNE and UMAP, they are best for visualization when you have non-linear relationship between the data. Okay, like for exploration and embeddings. And autoencoder is for feature compression. When you have large high dimensional data, you can compress that into lower dimensional, as we saw earlier, like 4 dimension to 2 dimension with the bottleneck layer. So that's where autoencoders comes into picture. So with that, I'll be concluding this video. Thank you for watching.